Okay, so I'll start now. Fine. So we'll start with. So today contents will be, as I already mentioned in yesterday. So it will be isometries, and we will talk about R linear, C linear maps, argument, and some properties of that one, and question based upon that one. Okay, so let us first talk about isometries. Okay. So So let f such that c to c be a function. Okay. So we say f is an isometry. Isometry if, so basically it is distance preserving map. Okay. So now with this definition, can you tell me some examples of isometry, some maps of isometry, which are isometry? Anyone? Any idea? Like if you take the rotation, they are isometries. Okay. So basically we will see that. So basically we will prove the following theorem. Just kind of. So every isometry is of the, so every isometry, so every isometry is of the following form. So it is z is going to az plus b, or z is going to az bar plus b. Okay, where mod of a is equals to 1 and b is any complex number. Okay. So we'll see the proof of this one. Okay. Okay, so let f be any isometry. Okay. Okay, and consider the following function. And okay, so if f is an isometry, so gz is equals to f of z minus, let us say, f of 0. Okay, so then g of 0 is 0. Okay, and g is also an isometry. Okay, I hope it is clear to everyone. So G is also an isometry which fixes origin. Okay. Now what we do? Now we define, okay, Hz is equals to Gz by G of 1. Okay. it is coming. Okay, so Hz is equals to Gz by G of 1, and obviously G of 1 is non-zero because G of 0 is already 0, and you can see the isometries are basically 1, 1. Okay. Now observe that H is also an isometry. Okay. Now H fixes, so H of 0 is 0 and H of 1 is 1, which fixes 0 and 1. Okay. Okay. So now claim is H is either of the form Hz is equals to Z or Hz is equals to Z bar. Okay. Now how to prove this one? Uh, so proof of the claim. So since H is an isometry, okay, so what we are having, Hz minus H of W is equals to H minus, oh sorry, so this will be Z minus W, okay, okay, so this will be Z comma W belongs to C, okay. Now this implies if you take W equals to 0, okay, if you take W equals to 0, so what will be H of 0 is 0, so this will be mod of H of Z is equals to mod of Z for all Z belongs to C, okay. This is easy to say this, okay. Now also if I take W equals to 1, so now if you take W equals to 1, so it will be Hz minus 1 is equals to Z minus 1 for all Z belongs to C. Let us say this is first, this is second, okay. So from 2 we have, now what we can do is Hz minus 1 whole square is equals to Z minus 1 whole square, okay. And this is nothing but Hz minus 1 into Hz whole bar minus 1 bar is 1 again, okay, and Z minus 1 into Z bar minus 1, okay. Okay, so okay, so here, so Hz into Hz bar minus Hz minus Hz bar plus 1 is basically equals to Z into Z bar minus Z minus Z bar plus 1, okay. Now here we can see that mod Hz is equals to mod Z, okay. So what does it mean? If you square it, this will be same. So Hz into Hz bar is equals to Z into Z bar. From 1 we have Hz into Hz bar is equals to Z into Z bar. So this thing, so this term and this term will get cancelled out, okay. So what we'll having, uh, 1 minus, okay, so 1 will also get cancel out. So hz plus hz bar is equals to z plus z bar. Okay, so what does it mean? Can you tell me? So this will be real part of hz is equals to real part of z. Okay, I mean this you can see here. If I want to be more rigorous here, so this is real part of hz plus I into imaginary part of z hz plus, again I have to use okay. So again I will do real part of hz into and minus image part of hz. So this will cancel out. So 2 into real part of hz is equals to 2 into real part of z. So this we will get. Okay, I hope this is clear. And again, and since mod of z is equals to mod of hz, what does it mean? It means that this implies imaginary part of hz is nothing but plus minus imaginary part of z. So is it clear to everyone? If you have any problem, just let me know.
Yes, sir.
Okay. Okay. So now we are having this thing. Imaginary part of sz is this, and real part of sz is basically this. Okay. So what does it mean? So what would be the form of hz? So basically hz is equals to z or z bar, isn't it? So so hz is equals to z or hz is equals to z bar. So we have proved our claim. Okay. Now what is hz? Hz is gz by g of 1. Okay. So hz is base equals to gz by g of 1. Okay. So gz will be g of 1 into z, or gz is equals to g of 1 into z bar. Okay. Now what is g of z? So g of z is fz minus f of 0. Okay. So fz minus f of 0 is equals to g1 of z. Okay. So basically fz is equals to g of g1 z plus f of 0, or fz is equals to g1 of z bar plus f of 0. Okay. Now this almost we got this form, isn't it? Az plus b or az bar plus b. Okay. The only thing is we have to prove that this a is nothing but its modulus is 1. Okay, unit modulus. So as we know that G is an isometry. Okay, so G is isometry fixing origin, fixing fixing origin. Okay, so it means that g of 1 minus g of 0 is basically equals to 1 minus 0 is basically equals to 1. Okay, so modulus of g of 1 is basically 1. Okay, so we got that g of 1 is basically 1. Therefore, so therefore fz is az plus b, or fz is equals to az bar plus b. Okay, so we have proved that every isometry will be of this form only, az plus b or az bar plus b. Is it clear? The proof is clear to everyone? Because we will see the questions on this one. Let me just write it down, the questions. So I hope this is clear. Anyone who have any doubt? Okay, so I assume that it is clear. Okay. So now we will start with the questions. Question based upon this one. Okay, so wait. So the question is, let I denote the set of isometries, denote the set of isometries of complex plane C. Okay, fixing origin C, which fix origin. So observe that I forms a group. I forms a group, and what will be the operation? Means under composition. Under composition. So which of the following is slash are true? Okay, so I will write it down the options. Okay, so first option is, suppose z is not equals to w are two non-zero complex numbers. Non-zero complex numbers. Okay, so the only isometry which fixes both z and w is the identity map. Okay, now the next option is same thing. Same thing means up to here the statement is same. There exist a non-trivial isometry. Non-trivial means other than identity. Okay, non-trivial isometry in I which fixes both z and w. Okay, Okay, fine. So yeah, next thing is, so here the only isometry, this would be in I. Okay. Now the next option is, okay, so next option is, suppose that z is not equals to w, are two, suppose z and w are two non-zero complex numbers, non-zero complex numbers, non-zero complex numbers such that w is equals to rz, so where r is non-zero real number. Okay, then there exists a non-trivial isometry, non-trivial isometry in I, which fixes both z and w, both z and w. Okay. 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 So what would be the solution for this one? Can you tell me? Any idea? Oh, yes. Yes, sure. Yes, Swami. I will. Yeah, yeah. I will share the notes at the end of lectures. I have to. Yeah, actually, I have to upload the previous assignment lectures also. Okay, that I will do. Yeah. So yeah. So what would be the answer for this one? So the first question. So let I denote the set of isometries of C, which fix origin. Now observe that I forms a group under composition. Now which of the following is slash are true? Now suppose z comma w are two non-zero complex numbers. Okay, two non-zero complex numbers. So the only isometry I which fixes both z and w is the identity one. Is it true? Okay, so I got one answer which says it is true. Okay, so let us see. So let us see the solutions. So for option A, let us see for option A. Okay. Why these lights are getting off? Okay. Okay, so once you see, yeah. So if you see option A, so let if you take z is equals to 1 and w equals to 2, okay, so can you tell me any isometry which fixes origin and also z and w other than the identity map? So let us take fz is equals to z bar. So this is again an isometry, but f of 0 is obviously 0. So this implies f belongs to I, and f of 1 is 1, also f of 2 is 2. Okay. So the answer is option A is wrong. Yeah. So this is not correct. What about option 2? Yeah. Yeah, they are real points. So that is the idea. So there exists a non-trivial isometry in I which fixes both Z and W. Is it always possible? Okay, so what we will do is, so, for option B, okay, so for this one what we have to do, now suppose, now since let us take any isometry, either it will be AZ plus B or it will be AZ bar plus B. Okay. Now since phi fixes origin, okay, so it means that so this phi of 0 is 0 means B is 0. Okay. So phi Z is either AZ or phi Z is either AZ bar. Okay. Now suppose Z naught comma W naught are two complex numbers. Okay. So phi of Z naught, let us take that is Z naught bar. Okay. And phi of W naught is equals to A W naught bar. So A Z naught bar is basically what? Since phi is fixing Z naught, okay, and phi is fixing W naught, so this is thing. So now this gives that if, so this gives that Z naught by Z naught bar is equals to W naught by W naught bar. Okay, and Z naught is not equals to W naught. Okay. Similarly, if we take phi Z is equals to AZ, okay, and we talk about phi of Z naught is equals to AZ naught, which fixing Z naught. So again, phi of W naught is equals to A W naught is equals to W naught. So this will give that A is equals to 1. Okay, so phi of Z is equals to basically Z. So this is identity only. Okay, so it means that if you have such kind of function, phi Z is equals to AZ, and it fixes two non-zero points like Z naught and W naught. In fact, so in that case, A is going to be 1. Okay, so it will be of this form only. But if you consider this function AZ bar, for this one, if you consider uh, function points which satisfies this one, okay. So if you consider the function set a point satisfying this one, okay, then this function will fix Z naught and W naught, okay, isn't it? Means it means that if we want to say that option B is not true, we have to find z naught comma w naught such that this this equality will not hold. Okay, so you take z naught or w naught so that this equality will not hold. So in that case, uh, oh sorry, so you take z naught and w naught so that this equality will hold. In that case, this uh, az bar will work, this non-trivial, so this will be non-trivial. Okay, and in this case a will be, yeah, whatever you will take, because this equality is hold. So is it clear? Okay, so what about option C? Can you tell me? So means this is also false. Okay, isn't it? So there always, so there ALWA always exists. Okay, so this is also false. I hope this is clear. Now what about the option C? Okay, so let us look at the option C. Yeah, once I'm doing this one, uh, it is always good if you guys also do it on your own. Okay, parallel to me. Okay, so for option C, let z is not equals to w be two non-zero complex numbers, non-zero complex numbers. Okay, such that, so w is equals to rz. Okay, where r is basically, okay, this is the only r, huh? Yeah, so r is non-zero real number. So if you picturize this one, okay, so, so let us suppose this is your z. Okay, so r into z either will be like this, so this will be your rz, let us say w, or somewhere here, okay, on this line only, w. Okay, is it clear? So what we can do here is that z, basically let us write r naught e to the power I theta naught. Okay, so r naught means, if you take z here, so this thing, your r naught. Okay, and this is your theta naught. Okay, now w is equals to r into z, which means r into r naught e to the power iota theta naught. Okay, so basically r, write it down, so r naught is less than r naught if r is less than 1 and r naught is greater than r naught if basically r is or greater than equals to 1. Okay. Now what you do, let let L be the line joining 0, W and Z. Okay. So what is your L? So either L will be this full one. So let me write it down. So either L will be this one, okay, or L will be only, I will write it as green, or this one. Okay. I hope this is clear. It depends upon R. Means if R is greater than equals to 1, so it will map Z to somewhere here. Okay. If R is less than 1, it will come here. Okay. So if it maps here, then we will consider this line L, and if it maps here, then we will consider this 0, W and Z, only this line. Okay. Is it clear? So the answer is reflection about the line L will be required isometry. Okay. And basically this belongs to I. So we know how to find a formula for reflection about line, like about Z axis. If you take, okay, so this is your Z and this is your reflection about this real axis. Okay. So basically what you will get, reflection about, so reflection of Z about real axis is nothing but Z bar. So it is a routine checkup that what would be the reflection about the line L. Okay. So it means that whatever the point is here will go to here. I mean, you can use the coordinate system to find the equation of the line. Okay. Did not get what you draw there, the long line on which Z and W. Okay, so let me write it again. So it is, let us suppose Z is here. Okay, once you do RZ, either it will take Z to here somewhere RZ, or what it will do, it will take Z to here somewhere RZ. Okay, if it takes here W and origin is here, suppose, so we will consider this line L. Okay, if it takes here W and suppose origin is here, we will take this whole line. Okay. So I hope everything is clear in this one. So option C is correct. We have found precise form. So the answer is yes. Okay. So this is about the isometries. So this is also called the Euclidean isometries. Euclidean isometries of the plane. Okay. Yeah. So let us move towards the next topic. Maybe I will talk about okay, so let us see the next topic. it is regarding the argument. So argument, okay. So just like eigenspace, let me see the comments. Okay, basically under that isometry line remains in, yeah, exactly, just like, yeah. So whatever the isometries you whatever the reflection you will take about a line L, so in that one that line will be preserved, so Z and W will be preserved, okay. So if you see the polar form, this will be mod Z naught e to the power iota theta, okay. So this is kind of your Z, okay. Okay, so this is your theta and this is your mod Z, okay. So so theta belongs to R such that Z is equals to mod Z e to the power iota theta, okay. So this is the definition of argument. So what is the definition of argument of Z? Argument of Z is basically theta belongs to R such that Z is equals to mod Z e to the power iota theta, okay. So Z should be non-zero obviously here, okay. Now if we consider a function, let us consider a function phi such that c minus 0, and obviously this will go to R, defined by phi of Z is equals to argument of Z. So is it even a function? Hello? Yeah, so it is a multivalued function kind of. Okay, so this is kind of multivalued function. What is our aim? We want to make it as a single valued function. Okay, so what we do for that one, so this is multivalued. Okay, so what we do for that one, we define capital ARG. Now, yeah, one thing we need to observe. Okay, so if any theta naught belongs to argument of Z, okay, so theta naught plus 2 pi I k such that k belongs to Z. So this also belongs to, so this also belongs to argument of Z, okay. So basically these two theta naught differ by a multiple of 2 pi, isn't it? Oh wait, sorry. So this would be 2 pi k. So 2 pi k, okay, also belongs to this one. K belongs to Z, okay. Yeah. So keeping this observation in mind, what we will do, we will restrict it some interval, okay, either 0 to 2 pi or minus pi, interval of length 2 pi. So let us say we will restrict it as minus pi to pi, and this we will call as argument of Z, okay. So argument of Z is basically theta belongs to argument of Z such that theta is in between minus pi to pi. Now just tell me whether phi such that c minus 0 to c, phi of z is equals to capital argument of z is function or not. Now this is a single valued. So argument of z is basically collection of all theta belongs to argument of z such that theta will be minus pi to pi. So there will be unique theta. Okay. So this is function, and also for each z there will be unique. Okay. Yeah. So now what can we say about the continuity of this function? Is it continuous? So where is it not continuous? Yeah. So if we see the points at negative real axis, if you come along this sequence here, and let us say you come along this sequence here. Okay. So this sequence, let us say Zn, wait, let us say Zn and Wn. Okay. So argument of Zn will tend to pi. Okay. So argument of Zn tend to pi. Let us say Z naught. Okay. And argument of Wn will tend to minus pi. Okay. But argument of Z naught is basically pi. Okay. So at this negative real axis, this is not continuous. Okay. Now similarly, okay, so basically everywhere else it is continuous. So basically it means that so Z is continuous on C minus 0. Okay. Fine. So this is called the principal branch of the argument. Okay, capital ARG. Uh, Again, like as I said, we can restrict this theta. We can restrict this theta to any interval of length 2 pi. Okay. Here I have when I am restricting minus pi to pi, I am calling it as a principal argument. Suppose if I restrict it in between theta 0 to 2 pi. Okay. Suppose, let me write it down here just for. So suppose theta is in 0 to 2 pi. Then what we can say about the continuity of argument of z, capital ARG? Then positive axis will be volumetric for yeah. So then argument of z is continuous on basically C minus 0 to infinity. Okay. So this is the case here. Okay. In fact, you take any theta, okay, and you take this line and you remove this line, argument will be continuous on C minus this line. Okay, so this argument, so this concept of the branch of argument is very useful when you define the branch of the multivalued function, which we'll see later, like log z, uh, root of z, those kind of functions. So this is the backbone for that one. Okay, so for argument, I don't see any question other than this one. Let me see. So all the fundamental things one can calculate regarding the argument. Okay. Yeah, let me again talk about an important concept. which is very important when we define the differentiability. Okay. So okay, then we will see some questions on this one. So R linear and C linear maps. Okay. Okay. So I mean regarding this one can we can write one question. Let me write it down regarding this one so that that will for the sake of completeness. Okay, so it is kind of compute 6 by pi capital ARG of minus 1 upon under root 3 plus I. Okay, so let us see the solution. So let z is equals to r e to the power eta theta, where r is positive. Okay, so 1 by z is nothing but 1 by r e to the power minus iota theta. Okay, so argument of 1 by z is equals to minus theta equals to minus argument of z. Okay, thus argument of minus 1 by under root 3 plus iota is basically equals to minus argument of minus root 3 minus iota, and which will be 5 pi by 6. Okay, so 6 by pi argument of minus 1 by under root 3 plus I is nothing but 5. So these kind of things one can see. Okay, so to talk about the R linear and C linear maps. Okay, so if you see, if we consider like let us say R2, or if we see, so R2 is nothing but such that x to R comma y belongs to R. Okay, and if we see the complex plane x plus iy such that x belongs to R comma y belongs to R. Okay, so one thing you can see here is that both R2 and C are vector space over R, isn't it? Okay, so if we consider any function t such that C to C, okay, so this will set to be R linear if t is linear, if you are considering C as a vector space over R. When considering C as a vector space over R. Okay, so C as a vector space over R basically same as R2 is vector space over R. Again, C is again a vector space over C itself. So that will be called C linear. Okay, so I hope it is clear now. Okay, so yeah, okay, so it is now what we will do. Okay, so this is the theorem which I will mention the book and you can go through the theorem. Okay, so a map, because this is quite important, to understand the real differentiability and complex differentiability of a complex function, how to differentiate between these two. So a map T such that R to R is R linear if and only if it is of the form Tz is equals to Az plus Bz bar, where A comma B belongs to C. Okay. Okay. So theorem 1, this we can theorem 1, and this we can say as theorem 2 is a map T such that C to C is C linear if and only if, okay, it is of the form Tz is equals to lambda z. So for lambda belongs to C. Okay. So I hope this is clear. So basically it means that every C linear map is a R linear map. Okay. So let me write the reference. So there is a book by Reinhold Remarque. I think Introduction to Complex Function Theory it is, I guess. No, so theory of complex functions. So in the content you can find, I mean you can see the content and you can go to that page number or something. So I hope this is clear. We will move towards the problem on this one. So is it clear to everyone? R linear and C linear map. So basically what we will see that once you have a complex function, that complex function can be written as in this form always, Az plus Bz bar. If it can be written in this form, then that function will be said to be R differentiable. So basically, if you recall the definition of differentiability in several variable, there we need existence of linear, okay, existence of linear function. So if that linear function is R linear, we call R differentiability. If that linear function is C linear, we call C differentiability. So C differentiability we will define as analyticity once it is in a neighborhood. Okay, so that we will see later. Maybe I think that is the content of week 3. Okay, so consider the problem. This question. So consider the map, okay, T such that R2 to R2 given by T of x comma y is equals to x plus 2y and minus 2x plus y. Okay. So which of the following statements are true? Okay. So first is T of x comma y is equals to 0 comma 0 holds for infinitely many x comma y belongs to R2. Okay. Second is T is a R linear map from R2 to R2, or you can say C to C. In that case, we will consider C as a R vector space over R. So third is when we consider R2 as C vector space, C, so let me write it down in the next place. Third option is when we consider R2 as C vector space, that is, so that is we are considering x comma y belongs to R2 with x plus iy in C. Okay, then T is C linear. Okay, this is the third option. The fourth option is, okay, so there is no fourth option. Okay, so let us look at the solution. So just let me know what do you think? So txy is equals to 0. What you will get? So x plus 2y is 0 and 2 minus 2x plus y is 0. So this will give x comma y is 0 only. Okay. So first is wrong. Yeah. So first is, so this thing is wrong. Now what about second one? T is R linear map from R2 to R2. Yeah, exactly. So this we can solve rigorously also. What you have to do is you take, so so to check this is R linear map, what we have to do, alpha belongs to R, okay, and we have to take x, let us say x1 comma x2, and y, let us say y1 comma y2, and we have to check these conditions. T, like x plus y should be basically equals to t of x plus t of y, and t of alpha x is basically equals to alpha into t of x. Okay, so this you can check, and in fact T is R linear. Okay, now what about C linearity? So like if you see T of x comma y is basically, okay, so C linear we have to consider this one. So let z is equals to x plus iy. Yeah, I will show this one how it is in C linear. So let's take z equals to x plus y. So T of x plus iy, which means T of z. Okay, so what is the definition of T of x plus y, which is, okay, so which is x plus 2y comma minus 2x plus y. So in complex it is nothing but plus I into minus 2x plus y. Okay, so this is nothing but x plus iy plus 2 y minus ix. So this is nothing but z minus 2I into x plus iy. Okay, so this is nothing but z minus 2iz, which is nothing but 1 minus 2iz. So this is T of z. T of z is equals to 1 minus 2iz. So there is no terms of z bar. This implies T is C linear. So to check C linearity, you have to convert to clearly see this, you have to convert it into Z and Z bar, and you have to see whether there is any Z bar term or not. Okay. So is it clear now? Just let me see another exercise is there.